Hello and welcome to this video on how to predict what the proton NMR spectrum of a compound will look like and why that might be useful. The way that we teach NMR interpretation, by interpreting the proton and carbon spectra to get the structure of a completely unknown molecule, isn't a real-life application of the technique. It would be quite unusual to have a molecule where you had absolutely no idea what it was. Usually we use NMR to check whether a chemical reaction that we've carried out has formed the expected product, whether it's gone to completion, and whether we formed any unwanted side products. To do this, we need to know what the NMR spectra of the starting material and the expected product look like, so that we can make a judgment as to whether our reaction has proceeded as we wanted it to. Let's look at an example. Paracetamol can be synthesized from the starting material para-aminophenol by acetylating it with acetic anhydride. If we want to know whether this reaction has been successful, we need to know what changes we're looking for in the NMR spectra of the starting material and the product. We need to be able to predict what the NMR spectrum of the starting material would look like and what the spectrum of the product would look like. In this case, we're just going to look at proton NMR spectra. So how do we predict the proton NMR spectra of these two molecules? We need to take into account the number of proton environments, chemical shift, integration, and coupling. The number of environments tells us the number of peaks we need to draw in our spectrum. The chemical shift tells us where we need to put those peaks left to right on the scale. The integration tells us the relative heights of the peaks, and we can draw those approximately to scale. Coupling tells us how many lines are in each signal, which depends on how many neighbouring hydrogen environments there are. Let's start with the starting material para-aminophenol. How many different chemical environments are there in this molecule? There's a plane of symmetry down the centre of para-aminophenol, and that means that some of the protons on the aromatic ring are in the same environment as each other. The NH2 protons are one environment, the OH proton is another environment, and then there are two sets of aromatic proton environments. We have 4 different chemical environments of protons in this molecule. This means we need to draw 4 peaks in the proton NMR spectrum. The next question is where to put the peaks. For this, we need to use a correlation table. We look in the correlation table for the shifts of each different type of chemical environment. There's an aromatic amine, and the shift for that is somewhere between about 3.3 and 4.0 ppm. There's an aromatic OH group, and the chemical environment for that is very broad, between about 3.5 and 7.7 ppm. We have 2 aromatic environments which will be somewhere in the region of 6 to 9 ppm. These lines represent the shifts I'm going to use for my spectrum, but if you put them anywhere within the appropriate range, that's absolutely fine. These lines represent the chemical shifts for each different chemical environment. The next thing to look at is the integration, or how many of each different type of proton there are. Protons 2 and 3 are each worth 2 hydrogens. Proton 4 is worth 1, and proton 1 is worth 2. So let's redraw the lines at approximately the right height ratios. Now we need to look at the coupling, or multiplicity, which is how many lines are in each signal. This depends on the number of neighbouring hydrogen atoms. Proton 1 is too far away from its nearest neighbour, which is proton 2, to couple, because it's 4 bonds away. Proton 1 will just exist as a singlet, because it has 0 hydrogen neighbours. Proton 4 is the same. It's too far away from its nearest proton neighbours to couple with them, so again that's just a singlet. Proton 2 has an ortho-coupling to proton 3, and a para-coupling to the other proton 3, so that will be a doublet of doublets. It's the same pattern for proton 3. It has an ortho-coupling to proton 2, and a para-coupling to the other proton 2, so again it's a doublet of doublets. This is approximately what we would expect the proton NMR spectrum of para-aminophenol, our starting material, to look like. Now we move on to our product, paracetamol. Paracetamol also has a plane of symmetry, so again the aromatic protons are in two different environments. We still have an OH group and an NH group, plus an extra methyl group. There are 5 different hydrogen environments, so we will need 5 peaks in our spectrum. To work out where to put the 5 peaks, we will again look at the correlation table. The aromatic protons and the OH group will be in approximately the same places as before. They might shift slightly due to the change in the amine substituent. Proton 1, which was the amine proton, is now an amide, and so will be expected between 5.4 and 8.5 ppm. There's also a new signal between 2 and 3 ppm for the methyl group. We have our 5 peaks in the correct places, and now we need to consider the integration. The 2 aromatic signals are still 2 protons each, and the OH is still 1 proton. Proton 1 has reduced from 2 to 1 proton. Proton 5, the methyl group, is worth 3. Here are the signals with the correct height ratios. Now we need to consider the coupling of the signals. The coupling patterns of protons 1 to 4 have not changed during the reaction, with 1 and 4 being singlets and 2 and 3 being doublets of doublets. The methyl protons are too far away from their nearest proton neighbour to undergo any coupling, so they are also a singlet. So this is what we would expect the proton NMR spectrum of paracetamol to look like. To see whether the reaction has been carried out successfully, we can look for the signals which are unique to the starting material and the product. The changes we would expect are the amine becoming an amide and the addition of the CH3 group. Here is the real proton NMR spectrum of para-aminophenol. How does it compare with our predictions? The proton signals aren't exactly where we drew them, but they're all within the correct chemical shift ranges. Integrations and couplings are all correct. This is the proton NMR spectrum of the product, paracetamol. Again, all of the signals have the correct integration and multiplicity. The OH and NH protons are slightly outside the predicted ranges. This could be due to inductive effects within the molecule. Now let's imagine that student X has attempted to make paracetamol from para-aminophenol. This is the proton NMR spectrum of their reaction product. Have they made the correct molecule? And is it pure? We can see 2 sets of signals, large peaks from the product and small peaks from the starting material, so in this case the product isn't pure. Thanks for watching, and look out for more content coming soon on the Analytical Science Tutor channel.